It feels like AI just exploded out of nowhere, right? One minute we're asking our phones for the weather, the next it's creating breathtaking art, writing its own code, and even passing medical exams. So, what happened? Why is it all happening right now? Well, the answer isn't some kind of magic. It's actually a revolution in engineering, and we're about to break down exactly how it all came together.
To really wrap your head around it, you just need to ask one simple question. How in the world did we get from this to this in just a few decades? I mean, the leap in what these systems can do is just staggering.
Okay, so let's just break this down for a second. Over on the left, you've got this program called Student from way back in 1964. You could give it a very specific structured algebra problem, and it would follow a very rigid set of rules to solve it. Super clever for its time, but that's all it could do. Now, look to the right. You've got GPT-3. You can ask it to write a poem, explain quantum physics, or draft an email for you. It gets context, it gets style. The difference here is just night and day. One is a hyper-specialized calculator, the other is a general-purpose thinking tool. And, that first approach, the one Student was built on, that was the original dream of AI. The whole idea was that we could make machines smart simply by hand-coding all of human knowledge into a giant perfect library of if-then rules. And for decades, this was pretty much the story of AI. You'd get these amazing, flashy moments, like Deep Blue beating Kasparov at chess. But then you'd also get these long, quiet periods. They called them AI winters. And it was when progress just stalled out, because that rule-based approach, it just couldn't handle the messy, unpredictable real world. Even Watson, which was so impressive on Jeopardy, was still, at its core, a gigantic database with some really, really clever rules for searching through it. And that brings us to the fatal flaw in all these early systems: brittleness. Think of them like a train on a track. As long as the input was perfectly aligned with the track, they worked great. But the second you gave them something a little bit unexpected, a typo, a weirdly phrased question, the whole thing would just completely fall apart. If a programmer hadn't thought to write a specific rule for that exact situation, the AI was totally lost. So what changed? Well, the whole paradigm shifted. Instead of trying to program rules into the machine, we started building systems that could learn the rules themselves just by looking at tons of data. And that is the modern AI boom. It wasn't one single discovery, but a perfect storm, the moment when three incredibly powerful ingredients finally came together at the same time. First up, we got the raw material: data. Massive, massive amounts of it. The internet basically digitized a huge chunk of all human knowledge and culture. All of a sudden, we had billions of web pages, photos, and videos. This data became the textbook from which a whole new kind of AI could learn what the world looks like, sounds like, and how we talk about it. And to give you an idea of the scale, check this out. ImageNet is a free public database with over 14 million images, all labeled by humans. This one resource became a total game changer. For the first time, researchers had a big enough playground to train an AI to actually see and recognize objects with shocking accuracy. It really kickstarted the deep learning revolution. Okay, but all that data is pretty useless if you don't have a way to make sense of it, right? And that brings us to ingredient number 2, huge breakthroughs in algorithms. We got new architectures like deep learning neural networks and especially the transformer architecture. These gave us the actual methods to find all the super complex patterns and relationships hidden inside those giant data sets. And just to help you grasp the ridiculous scale we're talking about here, look at this number. A parameter is kind of like a tiny little knob inside the network that gets tweaked and adjusted as it learns. GPT-3 has 175 billion of them. That's billions of connections all working together to capture the subtle patterns of human language. You could never, ever program that by hand with rules. It's just impossible. All right, so the final ingredient is the engine. I mean, training a model with 175 billion knobs on 14 million images takes an astronomical amount of number crunching. The secret weapon here, funny enough, turned out to be the Graphics Processing Unit, or GPU. It was originally built for video games, but its design was just perfect for the kind of math that powers deep learning. And if you thought the last number was big, just look at this: a 300,000-fold increase in the amount of computing power being used for AI training in just 7 years. This absolutely blew past Moore's Law. This explosion of raw horsepower is what finally made it possible to combine the massive data with the complex algorithms. It was truly the final piece of the puzzle. So with those 3 ingredients in place, the data, the algorithms, and the hardware, we could finally start building. But we're not talking about writing a simple app here. This is like building a massive, complex factory.
and it required a whole new kind of engineering discipline just to make it all work.
And this is what that modern AI production line actually looks like. You need these huge, robust pipelines to handle petabytes of data. You need complex systems to manage training jobs across thousands of GPUs at once. Then you have to figure out how to deploy that giant model so millions of people can use it. And you're not done. You have to constantly monitor it to make sure it's still working right as the real world keeps changing.
This is a completely different universe from traditional software development. You're not writing deterministic code. You're curating data and running experiments. And maintaining the system isn't about fixing bugs in your code. It's about detecting when the real world has shifted and your model needs to go back to school to get retrained.
So, the result of all this new engineering is this incredible explosion of AI systems that operate on a scale we've just never seen before, from planet-spanning models in the cloud all the way down to tiny little chips that fit in your pocket. So at the absolute highest end, you have something like AlphaFold. This thing tackled one of the biggest, grandest challenges in all of biology, predicting how proteins fold up into 3D shapes. It took a warehouse full of specialized computers running flat out for weeks, but it created a scientific breakthrough that's going to change medicine for decades to come. But then, and this is what's so wild, at the complete opposite end of the spectrum, you have TinyML. These are incredibly efficient little AI models that run on tiny, low-power chips. We're talking about a wildlife tracker that can spot a specific animal and run for years on a little coin battery. It's the same fundamental tech, just engineered for a totally different purpose. I mean, just look at this gap. It's staggering. A big cloud GPU has 16 gigabytes of memory. A tiny microcontroller might have 320 kilobytes. That's not a little bit less. That's over 1,000 times less memory. The engineering challenge of making useful AI work across this enormous spectrum, well, it's one of the great technical achievements of our time. Which brings us right back to our core idea. This whole AI revolution might feel like magic, but when you actually pop the hood and look inside, you find something that's honestly way more impressive. A brand new, powerful, and systematic field of engineering. Ultimately, what this all means is that a whole new discipline has really been born: machine learning systems engineering. It's the art and the science of taking those three ingredients, data, algorithms, and hardware, and reliably building systems that actually work, from the biggest data centers in the world all the way down to a $10 chip. All right, so let's just tie this all together. The AI explosion was not an accident. It was the result of a perfect storm: massive data, brilliant new algorithms, and superpowered hardware all converging at once. That convergence created a whole new engineering discipline to build and manage these incredibly complex systems. And the result is a technology that is powerful enough to solve grand scientific challenges and efficient enough to run on a tiny battery for years. You know, this is a truly remarkable moment to be in. For the first time in history, we've basically built an AI factory that's capable of producing intelligence on demand at scale. And that leaves us with the most exciting and maybe the most important question of all. Now that the factory is built, what are we going to choose to create with it?